So this time we will move on to circuits with a source and starting with RC circuits. Now, in reality, circuits often operate with a source. So it's not nearly possible that a circuit is just standalone. But we have those previous discussions about source-free circuits in order in just for us to understand how a circuit behaves intrinsically. So when the voltage source is suddenly applied, the RC circuit experiences sudden change in voltage. So unlike source free where our voltage would just die down, in an RC circuit with a source, it our circuit experiences voltage rise. So there's a difference in conditions between the moment where the RC circuit has no source and the moment where the RC circuit is suddenly connected to a source. So in our analysis with RC circuits with a source, we need to understand that there are two parts again. Uh, Two parts for our analysis, in which the part where the circuit responds naturally, and on the aspect where the circuit responds under the influence of an external voltage source. So as you can see in the diagram, we have the addition of a Vs, or the voltage source, and in this graph here, in the graph below, there are two voltages, VO and VS. VO is the one that is lower than Vs, which is at the top. So VO is the voltage of the RC circuit when the capacitor is initially charged. So remember VO in our source-free RC circuit. This is the voltage uh, which is produced by the energy stored. What do you call it? Let me reword that. VO is the voltage brought about by the stored energy in the capacitor, across the capacitor rather. But in the addition of an external voltage source, we have Vs. And Vs is the final voltage of the RC circuit after the independent source has been applied. So it is the final voltage, or the steady state voltage, after a long time. So as you can see in the graph, Vs is tangential to a horizontal line, because it approaches steady state, and by saying steady state, which it implies that our voltage does not change anymore with respect to time, so it flats up. So Vs will always be greater than Vo because of the additional influence of the applied voltage source. So Vs is something that we cannot see in our analysis with source-free RC circuits. So again, this implies that the complete response to solve RC circuit with a source has two parts. So the first part is the natural response of the circuit without without the influence of the independent source. So the natural response that we are talking about is the intrinsic behavior of RC circuit as if it is source free. So the complete response is uh, comprised of natural response, and this time has the addition of the forced response, in which this is the response that is brought about by the independent source. So if in terms of voltage, in the perspective of voltage of the circuit, the natural response can be seen with the V sub 0, and the forced response can be appreciated with the V sub S. So I've also placed here the equivalence of the complete response. So we have complete response Vt is equal to Vn plus Vf, in which our Vn is our natural response in which our circuit is source free, and our Vf is the forced response, which is the response brought by the independent source. So this is just our formula A. So this is one of two ways in which we can see or we can appreciate what sort of response is going on in our RC circuit with a source. So a complete response can be viewed as an addition of as a combination rather of natural response and forced response. But alternatively, we have formula B. We can also view the complete response as the sum of the transient response and the steady state response. The transient response is the temporary response of the RC circuit as the voltage increases in the voltage curve graph over here. And the steady state response is the final or the permanent response of the RC circuit after a long time that the RC circuit has peaked its Vs curve. So the Vs, that voltage at the steady state part. So alternatively, we can analyze the RC circuit with a source by adding the transient response or the temporary part, the response that dies out over time. The response that is temporary and the steady state response, which is the permanent or the final response of our circuit. So I prefer to use the latter because um, that is where we can obtain these formulas from the first order differential equations, which I'm gonna do next. So the complete response is given by Vt, which is equal to V of t rather, which is equal to V sub t plus V sub ss, in which our V sub t is our transient response, which is the voltage curve in this case. The curve part is our transient response, and this is given by VO minus VS, quantity E to the power of t over tau, and our steady state response, which is our voltage peak, the Vs. So our steady state voltage or VSS is practically equal to our Vs in this graph. So that's the final voltage. It cannot go high or lower than that. It flats out. So these are your given formulas, and at this juncture perhaps we can derive the differentiation. We can derive rather the formula for our RC circuit with a source. So assuming again that the capacitor is initially charged before the source is applied, before the independent source is applied at t is equal to 0. We have the voltage at the start, or our V sub O, is constant. The same condition. Then applying KCL, at the top node, yields, we have I, the capacitor current I sub C, plus the resistor current I sub R is equal to 0. So by nodal analysis, and definition of capacitor voltage, we can substitute IC to be C, the derivative of voltage in terms of time with respect to time, plus our IR in this case is equal to V minus Vs all over R, and we equate that to 0. Then we just have to rearrange the terms. So this is the indication that we've achieved the first order differential equation. By regrouping the terms, so it becomes ready to be integrated. We have dV over V minus Vs is equal to negative dt over Rc. So we will now integrate it, but this time we will have limits. We have the integration for the left side. We have VO from VO to V of t. Then for the integration in terms of time, we have to start from 0 to an arbitrary value of t. So this integration will yield us with ln Vt minus Vs minus ln Vo minus Vs is equal to negative t over Rc plus 0, because that's our initial value. Or we can rearrange this a little bit. We have ln Vt minus Vs is equal to Vo minus Vs is equal to negative t over Rc. So again, we need to eliminate ln. We have to use e power of ln Vt minus Vs over Vo minus Vs is equal to e to the power of negative t over Rc. So that eliminates our ln on the left side of the equation. We have Vt minus Vs is equal to Vo minus Vs is equal to over Vo over minus Vs rather is equal to e negative t over Rc, or e to the power of t over tau, which is our time constant. Our time constant being equal to R times c. Then we have Vt minus Vs is equal to Vo minus Vs e to the power of t over tau. Then our Vt is equal to Vs plus Vo minus Vs e to the power of negative t over tau. So this is now our final answer. This is the final formula rather. We haven't arrived with an answer yet. So we have two parts in this formula. This part over here is the transient response. And this part over here is our steady state response. So there you have it, the derivation of an RC circuit with a source. That is how we obtained this entire set of formula. Now, in the case of multiple resistors, you just need to find the Req, or the equivalent resistance, and to find the current, you just need to apply Ohm's law, and to find the power, you just need to apply the power formula. Now, you need three things, or three prerequisites in order to solve the RC circuit with a source. First off is the initial voltage V sub 0 across the capacitor, or the voltage at time when t is equal to 0. Second is the final voltage across the capacitor, or the final or permanent or the steady state voltage. And the third, of course, is the time constant tau, which is same with the source free RC circuit. So at this time, let us solve for a sample problem. So this problem requires us to solve for the complete response of V as a function of time. So the V that we are talking about here is the voltage across the capacitor. So there is only one capacitor here, but there are two voltage sources and three resistors. So we can solve this in two parts. The first part is when the switch is at position A, and then the second part is when the switch is at position B. So for switch at position A, we can immediately recognize that on position A we can neglect or discard the 4 kilo ohm and the 30 volts resistor circuit branch. So in order to clarify it, we need to redraw the diagram this way. We have 24 volts, the 3 kilo ohm resistor, then the 5 kilo ohm resistor, then our VC, or the capacitor voltage, in which in this case again we need to remember that under DC conditions our capacitor is analyzed or assumed as an open circuit. So we have two resistors here, but our capacitor voltage VC is actually equal to the voltage across the 5 kilo ohm resistor. So in order to solve that, we need to do voltage division. So VC is equal to 24 volts, the main voltage source, times 5k, because that's the voltage that is the same with VC, over 5k plus 3k, and our VC is equal to 15 volts. And our VC is actually equal to our VO, or voltage at time is equal to 0, so we will just write again the 15 volts. This is because the capacitor voltage does not diminish or change immediately. So right before moving the switch to position B, the VO, or the V sub C, or the current the capacitor voltage is equal to 15 volts. So the second part is for switch at position B. We will redraw the circuit once again, because the left side of the switch will not have a bearing for what the circuit will gonna look like. So we will redraw this time with the capacitor 0.5 millifarad. Then we have the 4 kilo ohm resistor, then the voltage source, which is equal to 30 volts. So from this simplified diagram, we can easily calculate for the time constant. We have value for R and C, so our tau or time constant is equal to RC times 4000 ohms times 0.5 millifarad. Our time constant therefore is equal to 2 seconds. So at steady state, so our steady state is defined as something that you can obtain after a long time, or after approximately 5 time constants the capacitor. What happens to the capacitor is that it then carries the voltage of the voltage source and becomes an open circuit. So when the switch is at position B, what happens after a long time is that our 0.5 millifarad capacitor will carry the same voltage as the 30 volt resistor. So that basically means that our Vs, or our steady state voltage, is equal to 30 volts. Now the complete response becomes Vt is equal to Vs plus Vo minus Vs e to the power of negative t over tau. We have 30 for our Vs plus our Vo. We find our Vo to be 15 volts. 15 minus 30 e to the power of negative t over 2. So our Vt, the complete response, therefore is equal to 30 minus 15 e to the power of negative 0.5 t, and that is our final answer in this case. So basically you're just substituting the values of the equation, values in the equation, and you will just leave the variable time t in the final answer, unless the problem specifies to us to calculate the value of voltage at a particular time. Like for example, if we are required to calculate the value of voltage at t is equal to 4 seconds, then you will just basically substitute 4 seconds in the variable t in this formula. So you can obtain a constant value of voltage at a particular time. So that's it for a sample problem for RC circuits with a source. Now moving on to our final topic for this lesson is RL circuit with a source. So this topic borrows so much from its predecessor, which is RC circuit with a source, Just like its predecessor, the analysis of RL circuits with a source also has two parts, and perhaps the difference between them is the natural behavior of the inductor itself. So there same with RC circuits, there is a difference in condition between the moment where the RL circuit has no source and the moment where the RL circuit is suddenly connected to a source. So as you can see in the diagram, we have three elements in the circuit. We have the voltage source Vs, we have the resistor R, and of course our inductor L. But in the graph below, we can easily notice perhaps that the final or the steady state value of the current is less than its initial value. So they are quite opposite with that of the RC circuit with a source, because in the RC circuit case, uh, the voltage source somehow supplements the voltage of the circuit, which increases the magnitude of the final voltage Vs. While in this case, the final current is less than IO, or the initial current. So just a heads up, there are two currents, IO and Vs over R. So IO is the current of the RL circuit when the inductor is initially charged. That is on the moment before the circuit is connected to a source. Vs over R is still a current value, and this is the final current of the RL circuit after the source has been applied. So it is the final current, or the steady state current after a long time. Vs over R will always be less than I sub 0 because of the exponential current decay of the stored energy in the inductor. So the inherent exponential decay of current is something that we can expect naturally from the inductor. So it is by nature of the inductor. When the current curve has flattened to the Vs over R, the inductor acts as a short circuit and the voltage across it becomes zero. So that's the point of short circuit. The entire source voltage Vs appears in the resistor R, because when the inductor becomes a short circuit, the only element that consumes energy is resistor. That's why we use Vs over R to represent the final current in the RL circuit. Just to, make it clear. The complete response as the sum of the transient response and the steady state response is given in this formula. So we have transient response, again, is the temporary part, the part where the current graph experiences curve, and the steady state response is when the current flattens to Vs over R level. So the complete response is given by both transient and steady state response. So the derivation of this formula is highly similar to RC with a source and the source free RL. So this time I will not give you a derivation of the formula using first order differential equations anymore. So instead, we will just directly substitute the formula to this given to what we have here. In the case of multiple resistors, we'll just use the equivalent resistance Req, and when finding the voltage, we'll just use Ohm's law again and power formula when calculating for power. And same is true, we have three prerequisites in order to solve RL circuits with a source. The first one is the initial current through the inductor, the initial current I sub 0, then the final voltage Vs, or the final current Vs over R through the inductor. So I'm sorry for this mistake. So Vs over R, just slightly lower than IO, and of course our time constant tau, which is same with the source free RL circuit, which is L over R. So at this juncture, let us solve a sample problem. Now in this given problem, we aim to solve for the complete response of a current as a function of time, or IT. So there are two moments in this switching sequence. So the first moment is when the switch is still closed, and the second moment is when the switch has been opened at the start, or when t is equal to 0. So just to write it down, when the switch is closed, both resistors 5 and 10 ohms are discarded. So both of these resistors are discarded because they are both in parallel to the switch, and when the switch is closed, both of these resistors are short circuited. Also, the inductor under DC conditions acts like a short circuit as well. So that leaves us that our IO is therefore equal to 6 amperes, because there is no element that remains on the original diagram, and so our current, being the only current source, is equal to 6 amperes. So let us carry that as our initial current. Now for our second moment, when the switch is opened, both resistors, 5 and 10 ohm resistors, are functional. So redrawing the circuit once again, we have 5 ohms, then our inductor on the top, we have 1.5 henries, plus another resistor over here, 10 ohms, then our current source, which is equal to 6 amperes. So there is something that is familiar with a current source placed in parallel with our resistors. This can in fact become by source transformation, will become a voltage source. So this diagram will become, redrawing it again, we have 1.5 henries, then the 10 ohm resistor becomes in series. The entire circuit rather becomes a series circuit. Then our voltage source is simply equal to current times resistor. So we have 6A times 10 ohms, we have 60 volts. So we obtained that by source transformation, which we have learned from the previous lesson. So since the 5 ohm and 10 ohm resistors are in series, we can add them in series. And that our Req in series is equal to 15 ohms. 15 ohms. Now our time constant tau is equal to L over Req. We have 1.5 henries over 15 ohms resistor. Then that is equal to 0.1 seconds. So after a long time, or approximately 5 time constants, our inductor carries the Vs over our current. So our steady state current ISS of T, or equal to Vs over R. Our Vs then is equal to 60 volts over Req, which is 15 ohms. We have our steady state current to be equal to 4 amperes. For the complete response, will look like just a simple substitution to the equation, to this equation right over here. We have I as a function of time is equal to Vs over R being the steady state, and then the transient response is equal to I0 minus Vs over R e to the power of negative t over time constant tau. Then we have Vs over R to be equal to 4 plus our I0 is equal to 6 amperes minus Vs over R again, which is equal to 4 multiplied by e negative t over 0.1 seconds. So our IT, our final formula for our current at any point in time, is equal to 4 plus 2 e negative 10t amperes. So that is our final answer, unless the problem specifies to us to calculate the value of current at a particular time. So in that case, you just need to substitute the time on the t variable in the formula, and then you can obtain a current which is a constant at a particular time. So again, this is our final answer, and just as easy as that, we can calculate time, calculate circuit analysis problems that involves time. So the differential equations are already derived for your convenience, so you don't need to do that anymore in our future endeavors. And hopefully I can send to you another assessment that is a combination of our lesson 6 and our lesson 7 before the week ends. So once again, we have just finished tackling our lesson 7, and I hope that if you have any questions, you can raise them on the Google Classroom. You can also chat me using the Hangouts or the Google Chat platform, or simply send me an email, whichever is more convenient to you. And if you find difficulty in viewing this video or recorded lecture, you can also pertain to our reference materials, and I will also send you a copy of the sample problem so that we can go back to them at your convenient pace. So once again, thank you so much for listening, and I hope that you take care, and stay strong.